In this chapter, we will be exploring the concepts of permutations and combinations. In this lesson, we will be exploring the concept of permutations.
So now we're going to throw some vocabulary at you, if you want to think of it this way. A permutation, okay, is a linear arrangement of a set of objects, and order is important. Okay, that's what makes a permutation a permutation. So just for example, really quickly here, if I do CAT and let's say TAC, these are two different permutations of the letters CAT, of the letters in the word cat. Okay, order makes a difference. In this order, it's the word cat. In this one right here, it's just not that word there, so it's different. So now, usually we're going to use factorial notation to help us out with this. So for example, the objects A and B have two permutations, okay? They could be A, B, and B, A here. Now, normally if you've got just two objects here, the number of ways you can permute them or arrange them would be 2 factorial. With 3 objects right here, the number of different permutations would be 3 factorial, 3 times 2 times 1. So you have 3 choices for the first object, then 2, and then 1, okay? Now, if you're going to take a set of objects and then you're only going to permute R out of N objects, then the notation that you use is a little different. We're going to use NPR. I'll zoom in a little bit more on this. NPR, okay, and that's going to be N factorial over N minus R factorial. Now I want to explain really quickly why that works the way it does. Okay, maybe I'll do it like this. Let's say, for instance, that you had 8 objects, okay, and we were going to arrange, let's say 5 of them. Okay, now I've got to zoom out here. Whoa, zoom out here. We're going to arrange 5 of them. So 1, 2, 3, 4, 5. Okay, I've got 5 different tasks here to accomplish. For my first task here, I'm going to put, there's 8 choices of objects, and then there are 7, and then there are 6, and then 5, and then 4. Okay, so 8, 7, 6, 5, 4. There are 5 different objects here. Now, I want you to think about this. Take a look at what we've got here, and notice that this is the beginnings of 8 factorial. Okay, but to finish that off here, that would be multiplied by 3, multiplied by 2, multiplied by 1. Okay, so that right there is 8 factorial. 8 factorial equals this right here. Except that I don't want all 8 of them. I only want those 5. I don't want this piece right here. However, that does look like the beginnings of an 8 factorial. So what I want to do here is I want to divide out this back end right here, this 3 times 2 times 1. Okay, because when I divide those out, that will leave me with that set of numbers that I actually want. Okay, the group of numbers that I guessed using the fundamental counting principle. Now that means this right here is 3 factorial. Okay? Now, let's think about these numbers. Now look at the question originally. 8 objects, and I want to arrange 5 of them. And my result ended up being the same as 8 factorial over 3 factorial. Now, I don't think it's any big surprise where the 8 came from, but where did the 3 come from? Well, the 3 comes from, if you've got 8 objects and you take away those 5, you've got that remaining 3 left over that I got to cancel out here. So really what this is, okay, this is 8 factorial over 8 minus 5 factorial. And that right there is the same as what we say 8 permute 5, or some people say 8 pick 5. However you want to look at it, that's where that's coming from. Now another way to look at this 8p5 notation here is that what this is this is related to factorials in the sense that what I'm going to do here is I'm going to start at 8 and I'm going to go down using, in a sense, like factorial notation, but I'm going to go down 5 factors. So 7 times 6 times 5 times 4. I'm going to start at 8 and I'm going to use 5 different factors starting from that value. That's another way of looking at 8p5 or NPR. Okay, going back to the notation over here, this NPR. But that's why it works like N factorial over N minus R factorial. Okay. When all of the objects are used in an arrangement, okay, now we've already seen this before, when you're arranging N objects, that is N factorial, and so NPN, we'll zoom in on that, NPN is n factorial, the number of ways you can permute or organize n objects. Okay, so we're going to use permutations anytime that we're dealing with order. If you change the order of a couple of objects, you change the result. That's not always true. Sometimes if you change, quote unquote, the order, you'll look at a scenario and go, well, so what? The order has nothing to do with it. Well, that's a different sort of an approach altogether. We call that a combination. For right now, we're dealing with things where order makes a difference. So, for example, if you've got a group of people and you're identifying, like, someone's the president, someone's the vice president, so on, well, order makes a difference. If you're talking about winning a race, for example, getting first, second, or third, order is important, right? You change the order, you change who won the race. Anytime they talk about arrangements, okay, they're referring to questions where order is important. So now we're going to take a look at a handful of questions dealing specifically with permutations.
How many permutations are there of the letters in the words Regina and Kelowna?
So for this question right here, we've started with the word Regina. Okay, how many ways can you permute the letters in that word? We'll take a look at how many do we got here? 1, 2, 3, 4, 5, 6. So one way to think about this is with the fundamental counting principle, right? You might have, for example, there's 6 letters to place here, so I've got 6 choices for the first one, and then 5, and then 4, and then 3, and then 2, and then 1, using the fundamental counting principle, or see this as 6 factorial, right? And if you go to your calculator, and I'll show you how to do this in your calculator in case you're not quite sure where you got to go here. To get 6 factorial, you'd enter 6. Then you'd press your math button right here, go over to the probability menu, and write down there number 4. Whoops, too far. Number 4, there's my factorial. So there are 720 different ways to permute, or different unique arrangements of the letters in the word Regina. Now let's take a look at the word Kelowna. 1, 2, 3, 4, 5, 6, 7. I don't need to jump through this hoop anymore. I will just go to my calculator, okay, and evaluate 7 factorial, and it turns out there are 5,040 unique permutations of the letters in the word Kelowna.
To simplify 10 factorial over 7 factorial, there are several approaches. Use your calculator, and then by cancellation.
All right, so let's start. We're going to simplify this with our calculator, so we'll pull this out here. Okay, and away we go. So 10, we already know where to go to get the factorial. Math over to the probability menu, divided by 7, and again math over to the probability menu. So 10 factorial divided by 7 factorial, and we get 720. So there's us using our calculator. 10 factorial over 7 factorial, boom, there we go. Now let's take a look at this by way of cancellation. So we're going to actually do, in a sense, kind of the algebra, the math of this, not really the algebra, but you get the sense here. So the way to do this is you look at these two numbers here. Which one of them's bigger? Well, I think it's pretty clear 10 factorial is going to be bigger. So when you expand 10 factorial out, somewhere in there you're going to bump into 7 factorial. Okay? So 10 factorial is the same as 10 multiplied by 9, the number 1 less, multiplied by 8, the number 1 less, multiplied by, now here's where the magic happens here, that's multiplied by 7. And then I'm going to keep going from here, from 7 all the way down. So this is going to be 7 times 6 times 5 all the way down to 1 here. So that's the same as 7 factorial. And I'm dividing this by 7 factorial. So those two will cancel. Now, bear in mind, 7 factorial divided by 7, okay, is not like the factorial symbol. I can't do that. That makes no sense. Okay? The notation doesn't work like that. In order to cancel like this, it has to be 7 factorial, 7 factorial. Okay? In order to get that kind of canceling. But then it's just 9 times 8 is 72, times 10 is 720, which is what we got when we used the calculator.
Express the following with factorials and evaluate. 10 permute 5, 9 permute 3, and n permute 3.
Okay, let's zoom in a little bit on this one here. So we're going to express each of the following of these permutation things here with factorials here. So 10 permute 5 is going to be 10 factorial over 5 I'm jumping ahead here. I did that a little bit maybe quicker than I should have. That would be 10 minus 5 factorial. That's what the expression tells us to do. So this will be 10 factorial over, well, 10 minus 5 factorial is just going to be 5 factorial. You'll do that subtraction first. Okay? And so really what this is remember, this means 10, okay, multiplied down, but we're going to use 5 factors. So 10 times 9 times 8 times 7 times 6. Okay? And now I'm just going to go to my calculator and evaluate that. Okay? And we get, and actually this is relatively large when you consider it, 30,240. Okay, so if you got 10 objects and you only grab 5 of them out of there and organize them, there's over 30,000 ways that you can do that. Now let's take a look here at 9 permute 3. That is going to be, by definition here, that'll be 9 factorial over 9 minus 3 factorial. Okay, so that's going to be 9 factorial over 6 factorial. Or another way to think about it here, that's just going to be like 9, but you're only going down 3 factors. So this will be 9 times 8 times 7. Okay, and I can just go to my calculator and evaluate that, and we get 504. Okay, now take a look at that. Look at the jump here. 9 pick 3. There's not much difference in terms of the numbers. 10 pick 5, or 10 permute 5 there. But we jump up from 504 to over 30,000. These things grow really, really quickly here. NP3 here, n permute 3 is going to be n factorial over n minus 3 factorial. Okay? Because remember what this is saying here. The way the permutation notation works, okay, NPR is left side factorial over left side minus right side factorial. So down here, left side factorial over left side minus right side factorial. And now I know we're supposed to evaluate. I really can't evaluate this if there's a variable in there, but I can simplify this. N factorial is going to be larger than n minus 3 factorial, and n factorial will be n times n minus 1 times n minus 2, and then n minus 3 factorial, which means it's going to go all the way down there to 1. I'll divide that by n minus 3 factorial, and so those will cancel here, those factors. And so we'll be left with n times n minus 1 times n minus 2, which we could expand that out if we needed to, or we could just leave it like that. Okay? Kind of depends on what the intention of the question is.
How many ways can all the letters of the word table be arranged using the fundamental counting principle and then using permutations?
So this is an idea we've talked about earlier here. So we've got the word table here, and there are 5 letters in the word table. So if we're going to organize these using the fundamental counting principle, that would be 1, 2, 3, 4, 5. I've got 5 different subtasks to complete here. What am I going to put in the first position? Well, there are 5 options. What would go in the second position? Well, now there's only 4 options. And then I got 3 options, and then I've got 2 options, and then finally just 1 more option. So just remember that these numbers here represent 1 choice out of that many possibilities. Now, that's one way to do this. Now, using permutations here, I might say that this is actually going to be 5 permute 5, or 5 factorial when all said and done here, because we're using all of the letters anyway, and that's just going to end up being 100. Whoops, sorry, you can't see that anymore. 120.
Using the letters of the word product, how many 4-letter arrangements can be made using the fundamental counting principle and then using permutations?
So this question is very similar to the one that we just did, except this time we're only going to use 4 letters out of the letters in the word product here. So there's 1, 2, 3, 4, 5, 6, 7 letters that we could use. But I'm only going to use 4, so that's going to be 1, 2, 3, 4. Okay, there's only 4 subtasks that I need to complete. The first letter here, I've got 7 options. And then after that, I've got 6, and then 5, and then 4. So that's using the fundamental counting principle. Now, using permutations, okay, the permutation notation, I'll just do it over here. Take a look at what this is. I'm starting with the number 7, so this is going to be 7 permute, and I'm only going down 1, 2, 3, 4 factors, so 7p4. Okay, and then I can just go to my calculator and evaluate that. And the answer is there are 840 different 4-letter permutations of the letters in the word product.
How many different permutations are there of 5 objects from a set of 7 different objects using the fundamental counting principle and using permutations?
Okay. And again, this is really similar to a previous question that we've done, except in this case here, we're not being told specifically what these objects are, although we do get the impression that that repetition here doesn't make any sense because we're dealing with, it sounds like physical objects here. So I've got to permute 5 objects, so that means I've got 5 subtasks to complete. 1, 2, 3, 4, 5. Okay. I've got 7 to choose from, so that's 7 options for the first object, and then 6, and then 5, and then 4, and then 3. And this will be the same as, now again, bear in mind how this relates to the notation, the permutation notation that we're about to use. Starting at 7, so there are 7 objects to begin with here, and then I'm going to permute, and I go down here 5 factors, so permute 5 of them, right? 7 permute 5, okay? And so that's going to end up being, when you go to your calculator, 2,520 different ways you can permute 5 objects out of a group of 7.
How many ways can a president, vice president, and treasurer be selected from a class of 25 using the fundamental counting principle and using permutations?
Okay, so here we go. So we're going to take a group of 3 out of a class of 25, but order becomes important here. I mean, just ask the vice president if that person wasn't chosen for the vice president, if they were chosen instead for the if they weren't chosen as president but were instead chosen as the vice president, would that make a difference? Well, yes, of course it would. If they're not doing it the way I think that should be done, it's going to be terrible. So yeah, order becomes important here. Now, using the fundamental counting principle, I've got 3 subtasks to complete here to get this group going. I have 25 people to choose from for my president, which leaves 24 for vice president, and that leaves 23 for my secretary or my treasurer. Now, that is going to be the same as, starting at 25, we're going to go down 3 factors. So 25 permute 3. Okay, and that makes total sense because this is like the beginnings, I should say, of 25 factorial, except I'm going to lose 22 factorial. Okay, that's where I start to cancel it out here. Now I'll go to my calculator and evaluate that, 25p3. Okay, and we'll get 13,800 different ways that we could build this little government out of a group of 25 people.
How many ways can 6 people line up if 2 of the people must be together, or if 3 of the people must be together?
Okay, so now we're going to look at a restriction on a permutation here. How many ways can 6 people line up if? Okay, well, first of all, let's take a quick look at this. Let's say you've got 6 people, and let's just label it A, B, C, D, E, F. Here are my 6 people, okay? Now, the first restriction here is that 2 of the people must be together. No matter where they stand, they got to be together. So just for argument's sake, let's say that that's A and B, okay? A and B stick together. Now, C is all by himself, so is D, E, and F. These people are all by themselves here. So let's just take a look at this. How many of these objects are we permuting? The AB forms 1 object, and then 2, 3, 4, 5. There are 5 different objects that I'm permuting here. So you could think of that as 5p5 if you wanted, or go back even a little bit further here. That's really just going to be 5 factorial, different ways that those could be permuted. Now, for every place that you put AB though, no matter where you slot them in, because they're going to be together, no matter how else you put everything around them, there's always going to be 2 different ways they could sit in their little pair. It could be AB or it could be BA. So for each one of those, we're going to multiply that by 2 factorial for the number of ways that this group all on its own could be permuted. Okay, and so all together here, when we multiply that out, we're going to get 240 different ways they could sit. Okay. Now, make this a little bit more interesting here. What if 3 of them have to be together? You got 3 of them that are best friends, this little group here. Well, let's just say, for argument's sake, that that's the group here, ABC. Okay. Well, now let's just take a look here. How many quote-unquote groups are we permuting? Well, we've got ABC, D, E, F. There are 4 groups that we're permuting here. And in this case, one of those groups has got 3 in it, and so how many ways can those 3, no matter where you put that group, how many ways can that group of 3 all on its own be arranged here, be permuted, and that's going to be multiplying by 3 factorial. So 4 factorial for the groups, 1, 2, 3, 4. Now, most of those groups are just groups of 1, but that's okay. And then there's one group here that's getting permuted in 3 factorial different ways. Now, putting that all together, turns out there are 144 different ways that we can do that. Okay, there you go.
Find the number of different arrangements of the letters in the word answer under each of the following conditions. Without restrictions, that begin with an S, that begins with a vowel and ends with a consonant, that have the 3 letters A and S adjacent and in the order A and S, or that have the 3 letters A and S together but not necessarily in that order.
All right, so first of all, before we jump into this without restrictions question, how many letters are there in the word answer? 1, 2, 3, 4, 5, 6. There are 6. Okay, so without any restrictions, okay, I'm not imposing any kind of external restriction on this. I've got 6 letters here. How many ways can you organize 6 objects? Well, that's 6 factorial, or if you want to think of it, it's 6p6. Either way, go to your calculator and you evaluate that. Turns out there are 720 different ways you can permute 6 different letters. Okay, 720 unique arrangements of those letters. Now, what if we insist, however, that it has to begin with an S? Now I'm going to start with that restriction, and this sort of becomes a fundamental counting principle problem. I've got a task to complete. That first task that I have to complete is putting an S there. Well, how many S's do I have to choose from? The answer is there's only 1. Now, beyond that, I have got 1, 2, 3, 4, 5 letters left to organize. And how many ways can I do that? Because that's my task. My first task is to put a letter up front, an S up front. Now, I can think of this as the next letter and then the next letter and so on. Or I can think of my next task being I have to permute 5 letters, which is 5 factorial. And so then 1 times 5 factorial would just be 120. I could do that, or I could do this with 5 different little lines there and fill those all in. Either way, it doesn't matter. Okay. How about that begins with a vowel and ends with a consonant? Okay, so here's what I got to do. I have to begin with a vowel, I have to end with a consonant, and I have to permute everything in between, all the rest of them. So how many vowels are there in answer? Well, there's 1, 2. There are 2. So for that first position there, I have 2 choices. Now notice this isn't 2 factorial, because I'm not putting both of the vowels up front. I have 2 choices, and I'm going to choose 1. That's what 2 by itself means without the factorial. I'm going to end with a consonant. Well, how many consonants are there? Okay, 1, 2, 3, 4. There are 4 consonants. So back here I have 4 letters to choose from to end this word here. Not 4 factorial. I'm not putting them all back there and permuting them. I'm only choosing 1 of the 4 consonants to put at the back here. Now, inside here though, I don't really care what order those letters come in. The only things we're concerned about here, or was concerned about, was the fact that the vowel had to come first and a consonant has to come at the end. Now that leaves me with 4 letters left over to permute there, okay? And so what I got to do here is write 4 factorial. That's the number of different ways you can permute those 4 objects. Now, in this case, the factorial is important because I do have all 4 objects there in between this vowel and this consonant. So I don't want the factorial here, I don't want it here, I do want it inside because that does actually represent all 4 of those objects in 4 factorial different ways. And when you multiply that all out, you will get 192 different permutations that start with a vowel and with a consonant. Okay. How about has the letters A and S and they're adjacent and in that order, A and S? Okay, well let's write this out here. This might help us out a little bit. So A N S W E R. Let's talk about what we're permuting here. Those 3 got to stick together, and then that's its own thing. This is its own group. This is its own group here. So that means I have got 4 different quote-unquote objects that I'm permuting. Okay, so that is going to be 4 factorial. And then notice that I've got, at that point here, normally what I would do is I would multiply by the number of ways I could permute this little group right here. But the truth is, the question says that it has to be in that order, A and S. There is only one way to order that, so I'm going to leave it right there. I'm just going to move that around as if it's A and S. And so that leaves me with just 24 different ways to permute that group. Now the next question, and I'm going to just make sure that we can see this here. The next question says that the letters A and S are adjacent, but they're not necessarily in that order. So we're still keeping them together as a group. So there are still 4 factorial ways of permuting that group. But I'm going to multiply this now by the number of ways that that group all on its own, no matter where you put it, that little group can be organized in 3 factorial different ways. Okay, so now we're going to multiply that together, and that gives us 144 different permutations where the letters A and S are together, but not necessarily in that order.
How many arrangements could be made from the word father if F comes first, or uncle if the C is first and the L is last?
So let's take a look here. So the restriction here is that F has to be first if we're permuting the letters in the word father. So that's 1, 2, 3, 4, 5, 6. 6 letters here. But I got to put F first. So I've got my first task is to put the F down. There's only one way to do that. Now, after that, my next task, if you will, is to permute the remaining letters here. Well, there are 5 of them. So there are 5 factorial different ways that could work, or 5 pick 5 or 5p5, if you will. Altogether, that's 120 different permutations of the letters in the word father, where F comes first. Now take a look at this one. How many ways can we permute the letters in the word uncle if C is the first and L is the last? Okay, so we've got 3 different tasks to complete here, if you want to think about it this way. C's got to be first. Well, there's one option for that. L has to be last, and there's only one option for that. Now there are 1, 2, 3, 4, 5 letters in the word uncle. I've already dealt with 2 of them, which means there's 3 left over, 3 factorial ways to permute the remaining 3 letters, and that leaves us with only 6 permutations of the letters in the word uncle if C has to be first and L has to be last.
How many arrangements of the following words can be made if the vowels must be kept together? Father and voice.
So here we go. So again, we're going to keep the vowels together. So let's write this out like this. So what I've got here is I've got A, E. I'm going to put the vowels together. Then I've got F, T, H, R. We're going to leave the letters A, E together. That's one group. And then I've got groups here of just 1 each. So how many groups am I permuting? And the answer is I've got 1, 2, 3, 4, 5. There are 5 groups being permuted here. Now, one of these groups, when I permute it, has got more than just one way that it works here. AE can be organized in 2 factorial different ways. Okay, and so what we're going to be left with here is 240 different permutations where we keep the letters, the vowels together. Now let's go over here. Let's take a look at this one and look at the word voice. Again, we're going to keep the vowels together. So O, I, E are all together, and then I've got V, C. So how many groups am I permuting? Well, 3 groups, 2 of which have only got 1 object in them, but I got 3 groups here. So that's 3 factorial for the groups. And then no matter where I go, or no matter where I put this, there's going to be 3 factorial ways that group can be permuted. And so 3 factorial multiplied by 3 factorial is going to give us 36 different permutations where the vowels are kept together.
How many numbers can be formed using some or all of the digits 5, 7, 2, and 3?
So for this question right here, hopefully it's written out correctly here. In order for this one to make sense, there has to be the indication that there's no repetition of the digits here, or else the answer actually ends up going to infinity. Now, but the thing that you got to clue into is that you're going to use some or all of those digits. Now, if you use all of them, again with no repetition, think about how that works. You're going to use all 4 of them. How many ways can you permute all 4 numbers there? Well, it's going to be 4p4, okay, which is 4 factorial. Or you don't use all 4 of them. You're only going to use 3 of them. So it's going to be 4p3. or you're going to use just 2 of those digits, and that becomes 4p4, or you're only going to use 1 of those digits. Okay, and that's what this thing looks like when they throw this little using sum or all. You don't know how many you're using at this point. So that's what creates these options here. So let me just run through this really quickly here. So this is going to be 24. Turns out this will be 24 as well. Okay, and the reason for this being 24 is because the difference between 4p4 and 4p3 is just that last digit 1. This is going to be 12, and then this is going to be just 4. Putting those all together, there are 64 different numbers that we can build with those digits.
How many 1-letter, 2-letter, or 3-letter words can be formed from the letters in the word pencil?
Okay, so now, before we answer this question, we got to figure out, well, how many letters are there in the word pencil? 1, 2, 3, 4, 5, 6, because there's 6 letters here. So how many 1-letter words could you pick? Well, I could do 6p permute 1, or that implies addition, or it could be a 2-letter word, in which case it would be 6p2, or it could be a 3-letter word, which would be 6p3. And again, I'm using addition here because I can't do these things simultaneously. A word can't have just 1 letter in it while at the same time having 2 letters in it. So I have to split these up into different scenarios here, and then I add them all up. And when you do that, the answer is going to be 156 different quote-unquote words that you get that have either 1 letter, 2 letters, or 3 letters.
In how many ways can at least one book be chosen from a set of 4 different books if the order matters?
Okay, so now the implication here, or not the implication, it's stated, order matters. So these are permutations here. So at least one book be chosen means from those 4 books I could permute 1, or I could permute 2 of them, or I could permute 3, or I could permute 4. Now take a look at that and look at 2 questions up here. That's the same pattern here. Turns out the result's going to be the same. There are 64 ways that you can reach in and grab 4 different books kind of off of a shelf here. If order is important, if the order that you stack them is important, then there are 64 different ways that you could do that.
There are 6 different flags available for signaling. A signal consists of at least 4 flags tied one above the other on a vertical pole. How many different signals are possible?
Okay, so if I'm going to use at least 4 flags out of 6 available here, and order matters, and we're assuming we're sending a signal here, so the order that you run those up the flagpole is going to make a difference. So to start off with here, you could arrange 4 of them, or you could arrange 5 of them. Now you can't do that simultaneously, so I have to split this up with an addition. Or I could arrange all 6 of them up there. And when you plug that in your calculator to evaluate that, you will get that there's 1,800 different signals that you can send with at least 4 flags.